So the third thing that we're going to look at for things that affect the stabilities of the transition metal complex is the Jahn-Teller effect. And the Jahn-Teller effect is a distortion that a molecule undergoes to relieve some degeneracy. So whenever you're filling in your last electron, if you have multiple options of which orbital you can put that electron in, and it's the same energy level, the molecule will distort to relieve that degeneracy, and when it does, it gives some extra stability to that complex. So any nonlinear molecule with a degenerate electronic ground state will undergo a geometrical distortion that removes the degeneracy. This also has the effect of lowering the overall energy of the complex. And the Jahn-Teller effect, this is particularly seen with copper 2+, so that's a D9. So we can really see that with these copper complexes. So it's really common to see the Jahn-Teller effect with D9 complexes. Because if we were filling in the electrons for 9 electrons, so let's say 1, 2, 3, 4, 5, 6, 7, 8, and our 9th electron, we have a choice of putting into the x squared minus y squared or the dz squared. So here we're just showing it in the x squared minus y squared. But the molecule can distort, and a lot of times you'll see this axial elongation. And when you remove the symmetry, you lower the symmetry of that molecule, the d orbitals will split in such a way that makes one of the orbitals more favorable than the other. So in this case, we're showing the dz squared lower in energy. And so that last electron will go into that dz squared if we're assuming a high spin case. So here we're looking at the copper hexaaqua species that we saw on the previous slide, but this is the crystal structure of it. And remember we said that it would distort to relieve that degeneracy. Notice that the bond lengths of the equatorial positions are 195 picometers. So these are shorter than the axial ligands. The axial ligands are longer, so you have this elongation along the axis of 238 picometers. So imagine pulling out those d orbitals, so you're lowering the symmetry of it, and that's causing a splitting of the d orbitals. Now with D9, you can't tell the difference between high spin or low spin, so it's going to come out the same way. But a D9 has a very strong Jahn-Teller effect. So this is why a lot of times if you see a copper 2+ complex, you better put in the back of your head, hey, is this a question about the Jahn-Teller effect, or can I expect some kind of distortions due to the Jahn-Teller effect? Now there are other arrangements that can have Jahn-Teller effects, and some of those are weaker and some of those are stronger. So let's say we have one d electron, and we're looking at an octahedral case. So if I have one electron, there's no high spin or low spin, but that one electron can go into one of these 3 orbitals. So I have a choice where it can go. So the molecule will distort to relieve that degeneracy and make one of those orbitals more favorable than the other. But that's a very weak minor effect. And now if we have 2 electrons, still there's no difference between high spin or low spin. You can't tell the difference. But again, I had a choice of 2 orbitals I could put it in. Now the 3rd electron, I have no choice because I need to follow the Aufbau principle. So I'm not going to promote an electron when I've still got a free electron or a free orbital right here. So there's not going to be a Jahn-Teller effect for a D3 complex. But now when we get to a D4, we can either have a high spin or a low spin. So let's create these other 2 sets. So if this is my low spin and my 4th electron, I've got 3 places for that electron to go. So I'm going to put it in the first one just to make my life easy. Now again, we're putting it into the lower levels, so this is going to be a weak Jahn-Teller effect. But if I've got 4 electrons at a high spin, 1, 2, 3, the next electron can go into one of these 2 upper ones. So I've got 2 choices. This is going to be a stronger effect. Now if I've got 5 electrons for the high spin, I've only got 1 spot, so I have no Jahn-Teller effects for a high spin. But for the fifth electron in a low spin, I've got two choices. So I have a weak Jahn-Teller effect there. Now for my sixth electron in a low spin, I don't have a choice where it can go. So it goes there. So I have no Jahn-Teller effect. But my sixth for a high spin will be in one of those three. So that's another weak effect. And then another for the seventh, another weak. And then for my seventh over here, that would be a strong. Now my eighth electron for either the high spin or low spin, there are no Jahn-Teller effects for a D8 system. Because my eighth electron has no choice, it has to go in this other one. And the low spin case has to go here. Sorry, the high spin case. So for the low spin D8, we have no Jahn-Teller effects for either the low spin or the high spin because we had no choice where the electron can go. But for a D9, remember from the previous slide, it doesn't matter which arrangement, 1, 2, 3, 4, 5, 6, 7, 8. Whoops, I counted too many. 1, 2, 3, 4, 5, 6, 7, 8. That last electron will go into one or the other, so it splits, and here we see that axial elongation, that bond gets longer to relieve that degeneracy, and so those orbitals will split into different energy levels. Now another thing that we can consider to affect the stabilities of transition metal complexes is hard, soft, acid, base theory. And if we're talking about hard, soft, acid, base theory, we've got to remember our definition for Lewis acids and bases. Remember, Lewis acids, you have an electron pair acceptor, and a Lewis base, you have an electron pair donor. So typically our Lewis acid is going to be a metal. So let's say we have a metal 2+. It is going to accept electron density from our Lewis base. So here we have just a generic ligand with a lone pair. And that lone pair, so that's the donor, it's going to donate electron density to that metal to make a coordinate bond. Now the gist of hard, soft, acid, base theory is that a hard acid prefers a hard base and a soft acid prefers a soft base. And when we're talking about hard and soft, hard is simply a molecule or an atom that has a very tight electron cloud. It's not very polarizable. You've got a high charge, or high Z effective or something that pulls that electron density tight, and it's very concentrated. But a soft acid or a base has a very fluffy electron cloud. It's not easily polarizable, and typically you're going to have low charge density. Since you're not going to have a high charge to keep everything concentrated, a lower charge, you're going to have a more diffuse electron cloud. And so on the next slide we'll give you some examples of some hard and soft acids and bases. Notice that our hard acids, remember these are going to be your metals, and specifically things in a high oxidation state, so very high concentrated charge. So something like iron 3+, cobalt 3+, nickel 3+. These are hard acids. These are going to accept electron density from our ligands. Now the hard bases are going to be things like oxygen containing ligands or halogens. So fluoride, think of very electronegative. It's going to have a very small, tight electron cloud. Now there are some things that are soft. So let's look at the soft acids. Those are going to be things with low charges. So copper +1, silver +1, gold +1, or also very large metal ions. So mercury is a very large metal ion, so it's got a nice soft fluffy electron cloud associated with it. And of course there are things in the middle that are kind of borderline. It's not too hard, not too soft, but somewhere in the middle. And some examples of some borderlines would be iron 2+, or cobalt 2+, or nickel 2+. And some examples of some soft ligands or some soft bases. These have very fluffy electron clouds, so like iodine, remember that's a very has a very big radius and only a -1 charge. So you've got a lot of area to spread that negative charge about. Also, sulfur-containing ligands. Those are typically soft ligands. Now your soft bases and soft ligands, your borderline bases or your borderline ligands, these are typically going to be a lot of your nitrogen containing compounds, or something that is in between the hard and the soft. So here we have an example of demonstrating the hard-soft acid-base theory and explaining how hard-soft acid-base theory can explain the stability of some complexes. So we're going to look at the fluoride ion. So fluoride is a hard base. So you've got a very tight electron cloud around that fluoride. And iron 3+ is considered a hard acid. Whereas the silver, remember, it's got a lower charge, so the electron is going to be fluffy, so this is going to be a soft acid. So the question is, would we expect fluoride to want to bond to the silver +1 or the iron 3+? So based on hard-soft acid theory, we would predict that the iron, which is a hard acid, would want to bind to the fluoride, which is a hard base. And this is reflected in the formation constants of these compounds. So the formation constant of the iron fluoride complex is 10 to the 6th. Now this is much, much larger than the formation complex of the silver fluoride complex, which has a formation constant of 10 to the 0.4. Thus illustrating that a hard base would much rather bond with a hard acid. Now something else that we can use to explain the stability of transition metal complexes is the basicity of the ligand. So more stable complexes are formed when a metal ion binds to a strong base due to increased electrostatic interactions between the metal and the ligand. And this is going to be especially true when highly charged metal ions such as copper 2+ or iron 3+ binds with a strong base. So remember that coordination bond is, it's got some ionic character and it's got some covalent character. And so when you've got a more basic ligand, it's going to want to bind, you've got more electrostatic interactions with your metal, and when that metal is even highly charged, it's going to be even stronger. And that also kind of reflects what we saw with the hard acids binding with the hard bases. So here we have some examples. Here we have some ligands, and if we compare the basicity of the ligands, here we have the least basic ligand as we go across to the most basic ligand. And if we can compare the log K value, so the formation constants of these ligands with a metal, so let's just look at the zinc right here. This is the zinc complex of the least basic ligand, so it has the lowest log K value, so this is going to be our least stable. But as we bind the zinc to more and more basic ligands, the formation constant increases. So the stability constant on the y-axis versus the acidity constant on the x-axis, and the graph shows an increasing in stability as the basicity of the ligand increases for a series of metal ions. And that's a general trend. So you can see all of these metal complexes, except the magnesium, see this increase. Now also, it's not just the basicity of the ligand that affects the stability of the complex, also the pH affects the stability of the complex. So the higher the pH, the more stable the complex is. Now remember, the ligands are Lewis bases, and the less available protons when you've got the higher pH, because the higher pH you consumed the protons, that means that the ligand will have less competition for their donor electrons. Because if the ligand is protonated, then it can't complex the metal. And the stability of that complex is going to be proportional to the fraction of ligand that's in the correct form. So that's in the deprotonated form. So let's imagine we have two reaction systems. One where we have lots of protons in our system compare to our metal, and we throw in our ligand. Let's say our ligand has a -1 charge. I'm just making this up. And then on the other side, we've got a solution at a higher pH, which means a lower proton concentration. So I'm just going to add a few more metal complexes to both sides. So in this first situation, when the pH is lower and I've got more protons around, those protons are more than likely to bind to the ligand. And if the protons are binding to the ligand, they're masking those lone pairs, and then you can't get an interaction between the metal and the ligand. Now, if you've got lots of metal around, a few protons, then if you've got a ligand with some lone pairs, that ligand can then bind to the metal. So you've got fewer competition with something for that ligand to interact with. Let's show you some data to look at. So here we see some data of how the pH affects the stability of transition metal complexes. And in this graph we show the stability of a EDTA complex. And so this EDTA complex is ethylamine diamine tetraacetic acid. So I'm going to draw that out for you because that's a hexadentate ligand. So you've the two nitrogens that are linked by a carbon chain. And off of each nitrogen, you've got a CH2, CO, you've got these carboxylic acid groups. So CH2, COO minus, CH2, COO minus. So you can see if the pH is very low, lots of protons, you'll protonate those carboxylic acid groups. But if the pH is higher and you deprotonate those carboxylic acid groups, those create good points of attachment so that those lone pairs on the oxygens, and each of those oxygens have a minus charge on them, those can then bind a metal complex and create a more stable complex. So the pH affects the stability of the complex because you have a competition of the metal, the positively charged metal, and the protons with those lone pairs on the ligands. So I'm going to stop my presentation there. So this is the second portion of these slides. And on the third set, we'll look at the denticity of the ligands and the chelate effect.